Hello, USHS students. Today, we're going to take a peek at the periodic table and try to identify some properties therein. Please have your periodic table handy. It's going to come in useful when you do the quiz at the end of this. So, some objectives that you need to pay attention to while we go through the guided notes would be how the periodic table has changed through time, some of the names, some of the dates, where that periodic table is broken up in terms of metals, nonmetals, metalloids, some properties of those particular elements, how we would explain how the periodic table is arranged, what kind of properties there are, the number of valence electrons there are, how ions are formed as a result of those valence electrons and how they change. So all of these things are items that you're going to find on the quiz, so please pay attention to these specifics. All right. The terminology that we're going to use are right here. We're going to be describing all of these different vocabulary words. So if you come across something that you're not familiar with, please make sure that you write it down so that way you can go back to it if you need to. All right. Now, let's start off with the history of the periodic table. The history of the periodic table, it has changed as we have had new technology and new elements being discovered. All right, in the early 1800s, we didn't have a very large, extensive list of elements known at that time. John Dalton didn't have every piece of modern equipment that we do today. A lot of the elements that we know today came from refining ores, discoveries that were being made. And then from those new elements that were discovered, we found that there are certain properties that repeat themselves. All right. And what we did is we started to group up those properties based on what kind of characteristics they had. Like, for example, if we look at the alkali metals, we have lithium, sodium, potassium, all the way down to francium. All of those alkali metals are in group 1A. They all are shiny metals. They all conduct heat and electricity well. They all react violently with water. Now, why is that? Because they all have one valence electron. And they're metals. Metals, they want to give away electrons easily. And sure enough, once you put any of these alkali metals into water, let's take sodium, for example. You throw sodium in the water, it wants to get rid of that electron so rapidly that the sodium binds with the water, forming sodium hydroxide, freeing off hydrogen gas. Now, in the process of doing that, it produces a lot of heat energy. That heat energy ignites the hydrogen gas, and you get an explosion. And that's the same for all of those alkali metals. Then when you look at the alkaline earth metals, calcium, strontium, barium, those are all examples of metals. They want to give away electrons. That's what defines a metal. So they want to give away electrons. So they also are good conductors of heat and electricity. But in terms of metallic properties, these elements are not as metallic as what the alkali metals are. See, as you move from left to right across the periodic table, the metallic properties start to decrease. Why is that? Well, which ones want to give away their electrons the easiest? The alkali metals. So those are the most metallic elements on the periodic table. And then as you move from left to right, you go from metallic elements to non-metals on the right-hand side. All right. Now, that right-hand side, those non-metals, let's take a peek at the halogens. The halogens, fluorine, chlorine, bromine, iodine, all of those have different properties than what the metals have. See, all of these have 7 valence electrons. It's not easy to strip away 7 electrons. Okay, what we'd like to do with those metals or even the non-metals, we'd like to have 8 valence electrons. In fluorine, chlorine, bromine, iodine, in order for them to have a stable electron configuration, it's got to do one of two things. It's got to lose 7 electrons or it's got to gain 1. And as I said, losing 7 electrons is extremely difficult to do. It'd take a lot of energy to accomplish that. So the halogens, instead, what they want to do is they want to gain electrons. They want to form what's called an anion. All right, now these, if we're looking at properties of the nonmetals, these things, they're not going to conduct electricity very well. They're not going to look at conducting heat very well. And we'll look at some other properties in just a moment. Okay, so that periodic table, when was one of our first periodic tables? Well, that was back in 1864. Now I'm highlighting that because that's one of your answers to a quiz question. So again, pay attention to the terminology, the names, and the dates. Okay, so if we're looking at 1864, we don't have all the elements that you have on your periodic table. So what John did is he arranged his elements that were known at that time based on increasing atomic weight. Why not protons? Because we didn't know that there were different numbers of protons inside of the nucleus. We didn't know that. Okay, so we couldn't use that method. What we could use was atomic weight. Now, as he was lining these elements up, and you can see his periodic table in the lower left right here. All right, now what we saw is that as we started to organize these based on increasing weights, that we had repeating properties that occurred. See, we just said a second ago that sodium, lithium, potassium, all of those shared similar characteristics. So what Newlands did is that every 8th element, he found that properties started to repeat themselves. So what he did is he just put them in the same column. The elements that had the similar characteristics, he put them all in the same columns. But what he noticed is that there were problems that occurred after that 17th element. Okay, so in attempts to force the other elements to behave that same pattern, he called it the law of octaves, but that really didn't work out. Okay, so where did we go from here? Well, Dmitry Mendeleev in 1870. What he did is he organized all of the known elements at the time onto cards, kind of like a deck of playing cards. You have a deck of playing cards, you have the 2 all the way to the ace, all right, in each suit. Well, what he did was he took all of the elements and he put down properties of those elements onto the period or onto these cards. And then he started arranging these cards based again on atomic weight because, well, we didn't know about the number of protons, right? Now, what he found is that as he was laying these elements out into these vertical columns, there were empty spots that were showing up. Now, those empty spots in those vertical columns, one might say, well, there's a mistake here. No, there's not a mistake. What he said is that these empty spots inside of the periodic table he was developing, we had elements that just had not been discovered. So there are question marks. And Mendeleev was extremely intuitive. What he said was that these blank spots on our periodic tables, that those blank spots were just elements that weren't discovered, and that he said that these elements, when they were discovered, they would have distinct properties as other elements in that same group. And sure enough, when we're looking at these elements that were not known at the time, they did, once they were found, they did have the exact same, well, I don't want to say the exact same, but extremely similar characteristics as to what he was predicting. All right, so what would some of those be? Well, if we're looking at our columns that I just had there, if we're looking at the same column as aluminum and silicon here, these columns, those blank spaces, what were they later discovered as? Gallium and germanium. And gallium and germanium, they had the properties that Mendeleev had predicted. Now, this periodic table that Mendeleev came up with, it wasn't free of errors. See, when we're talking about arranging his periodic table based on increasing atomic weight, one of the big problems that came up was that there are discrepancies when we are looking at increasing atomic weight. See, let's start at iron here. You have 55.85. You go to cobalt, 58.93. Now, Mendeleev's table would be great. That's increasing atomic number. All right, or I should say weight. I don't want to say number. All right, so it's increasing atomic weight. Now, when you get the nickel, what happens? 58.71. That doesn't match up with what Mendeleev had. Okay, so if we were to go by this, these two elements would be flip-flopped like that. All right, but it didn't match up with the properties. So there were some issues that Mendeleev had with his periodic table, but for the most part, it was an improvement off of what Newland's was. Okay, so let's move on. We have our modern periodic table, what we were just looking at a moment ago. The modern periodic table, why is that so much different? Well, see, Henry Moseley, through the process of X-ray diffraction, he found a stair-step increase in the frequency when he was looking at each successive element. See, what he said was that this change in the frequency of each element as we increase it by one element from one element to the next, all right, is that he said that that increase, that stair step that occurred, was because we had one more successive positively charged proton in the nucleus. So that altered Mendeleev's periodic table. All right, not drastically, but what we do is by looking at not the weight, but the atomic number, all of a sudden, this issue is gone. Okay, now our stair step, our increase in frequency goes 26, 27, 28, 29, 30. That answered all of our problems that we had. And that's not just cobalt and nickel. There are several spots throughout the periodic table that we have these similar discrepancies from our mass from one element to the next if we try to increase from one to the next. So that atomic number, where we're typically going to find that is in the top portion of each cell on the periodic table. Now, don't get that confused with the decimal value right here. The decimal value is what we call the weighted average of all of the isotopes of that element. All right, so weighted average of all the isotopes, that's not how our current table is arranged. Instead, we want to use the atomic number. Now, atoms that we have similar properties to, like the alkali metals, the alkaline earth metals, the halogens, what we're going to see is that the vertical columns all have similar characteristics. So all the alkalis are the same, or act the same. All the halogens act the same, okay? So try to identify when you're looking at this, especially when you do the quiz, what the information in the cell is actually telling you. And you're going to see on my table, I help you out with that by this key right here. All right, so all of those numbers, all of those charges and letters and symbols, all that stuff is right there for you. You just have to take a peek. So how is our periodic table arranged? Well, first off, I want to point out that if you're looking at my periodic table, there's going to be a little stair step, and we'll show it in just a moment. But to the left of the stair step, those are generally going to be your metals. Now, metals, they like to give away electrons. They're on the left-hand side of your periodic table. We would describe these as being in elements or groups. These elements would be in groups 1 through 12, and then some of them are in 13 through 16. And then to the right of that stair step, you're going to have your nonmetals, with the exception of hydrogen. Hydrogen's just an oddball. It's like the black sheep of the periodic table. And that's why I colored hydrogen cell as if it were black. because it's the black sheep. It doesn't fit. It's the oddball in the periodic table. But all the nonmetals are on the right-hand side of the periodic table. And usually you're finding those between groups 13 through 17, and then all of group 18 is the nonmetals. All right, so what am I talking about here when I say the stair step and things left and right of it? Well, if we take a peek right here, here's your stair step, okay? To the left of the stair step, all of these are metals. All right, now the metals, they want to give away electrons. They're good conductors of heat and electricity. On the right-hand side, all of these right here, these are non-metals over here. These, they're brittle. They have low melting points. They want to pick up and gain electrons. Now, one thing I just noticed, and I want to make sure that I don't include this. See, I had the arrow right here that was into the light blue. I don't want to do that because the elements that are on that stair step, these are what we call the metalloids. All right, the metalloids, they share characteristics of metals and nonmetals. Now, I did say a moment ago that hydrogen is the oddball. See, if we say everything to the left is a metal, hydrogen's on the left. So is hydrogen a metal? No, it's a gas. So why isn't it on the right-hand side? Well, that's why I put this right here, because one could argue that hydrogen, it has one valence electron, so that's why it belongs in group 1. But then somebody else might argue, well, hydrogen needs to gain 1 electron, just like all the halogens, so it should fit there, and it's on the nonmetal side. The argument could go both ways. So we really don't look at hydrogen in terms of the group it's in based on its properties, because it's not a metal. It is a nonmetal, but we could put it, see, it's just different spots. It's that weird element, okay? Now, let's take a look at just another picture, another image of this without all the symbols, numbers. When you have anything that's to the left of the stair step, all of these are the metals that want to give away electrons. They form what we call cations. There's one of the terms that we're going to come up with in just a moment. And then we have all of these on the right-hand side. Those are the things that want to gain electrons or form anions. And then you got your metalloids right in the middle. And those, they could gain or lose electrons. A lot of those, they want to share electrons versus giving up and gaining. Okay? Now, let's take a peek at the next thing. Metals versus nonmetals. Metals versus nonmetals. Metals, as I said, want to give away electrons, and therefore their chemical and physical properties are similar. Metals, if they want to give away them, they're good conductors of heat and electricity. They have lustrous properties. They want to be shiny in nature, etc. And we'll look at more of those in just a moment. Then we have nonmetals. Nonmetals, they're more of a dull, vitreous color. They don't conduct electricity well. So what you will find in terms of properties, that when we're looking at metals versus nonmetals, they're opposites of each other. So if you have a metal, it's nice and shiny. And then if you have a nonmetal, it's dull or vitreous in color. If you have high densities for metals, that means you have low densities for nonmetals. You have high temperatures, you have low temperatures. You have high boiling points, you have low melting points. Ductile elements, that means it can be drawn out into wires. So copper is great, you can draw it out into wires. But try to take sulfur and pull sulfur out into a wire, it's not going to happen. What you do is if you try to pull sulfur out into wires, it's going to break apart. It's brittle in nature. And then if you take a piece of copper or a piece of aluminum, you can bend it in all kinds of different shapes. You can pound it flat. It's malleable. Good electrical conductors. Nonmetals, not good conductors of electricity. So those are just some properties, but the idea is that they have different characteristics. So how about those elements that are right in between the metals and the nonmetals? Those are things that we call metalloids. The metalloids are found on that stair step that I showed you on the periodic table. So let's look at one of those metalloids on that stair step, silicon. Silicon, what we use silicon for is in your computers. They're semiconductors. Now, what exactly is meant by something that's a semiconductor? It's something that can conduct heat and electricity under certain conditions, but they don't conduct that heat and electricity as good as what metals are. All right, now when we're looking at those semiconductors, they can either be dull or they can be shiny. So they might be dull or they might be lustrous. All right. And they can exist in different types of forms. They can be ductile or not. They can be malleable or not. They can gain or lose electrons. But when we're looking at these, they have properties that are similar to the metals, but not in all cases. And they have properties similar to nonmetals, but not in all cases. So that's why we call them the metalloids. They share characteristics of both. All right, so let's take a look at the periodic table, how it's arranged. Now we know from before that our periodic table, Henry Moseley rearranged it based on the increasing number of protons that you find in the nucleus. But what we're also going to find is that in that arrangement of those atoms as we move from left to right, that the atoms with the similar number of valence electrons, those outermost electrons, are going to be found in the same vertical columns or groups. That's not by coincidence. See, the number of valence electrons determines what the properties of that element are actually going to be. So when you're looking at the alkali metals, every single one of them will have one valence electron. They're all going to react the same way. And then when you're looking at elements in the same period or horizontal row, the ones that have the same number of valence electrons, they're going to be, at the same energy level. So if you're looking at sodium and then lithium and potassium and you're looking at francium, all of those, regardless of what energy level or what period they're on, they always have the same number of valence electrons. All right, elements which are in the same horizontal row, we call those periods. And then, as I said, the arrangement on the vertical columns would be the groups. Now we number those groups from 1 to 18, numbering every single column across the table. But we are going to break those 18 elements up into two distinctive groups, the group A elements and the group B elements. What we have here would be our periodic table, and to make sure that you understand which are the periods and which are the groups and what we mean by each one of these, the periods are the different rows on the periodic table. So you're going to find from top to bottom on the table, you're going to see them numbered on the left-hand side. So in period 1, n equals 1, remember this is the principal quantum number right here. That's going to tell you the number of energy levels. So hydrogen and helium, they're only going to have one energy level. In n equals 2, principal quantum number 2, second row, what does that mean? This one has 2 energy levels. And then this one has 3 energy levels, and so forth and so on. And the groups on the periodic table, these are going to be arranged 2 different ways. We can look at it in terms of groups 1A, 2A, all the way over to group 8A. All right. Now, on my periodic table, this is how I have it arranged. And the reason for this is because when you're looking at group A elements, the column number is going to tell you the number of valence electrons. Like these guys right here, they all have one valence electron. These have 2, 3, 4, 5, 6, 7, and then these right here, those have 8 valence electrons. Now, if those are the group A elements, all of these right here, these would be the group B elements. And there's different rules that apply to that, and you should remember that from when we were doing the electron configurations. The other way that you can number the groups on the periodic table, if you don't separate them up into the group A and B elements, you just number them from left to right, all the way from 1 to 18. That's the other way that you could do this. Okay, so the groups, they tell you what kind of characteristics they have. All of these guys right here, the alkali metals, they all react very violently when thrown in the water. They want to give away electrons. All of these guys right here, the halogens, there are salt formers. They react violently to pull electrons to them. Okay, so let's move on. So let's look at some more characteristics on the periodic table in terms of groups. When you're looking at the groups on the periodic table, it's pretty easy for the first two groups, if we don't group them into A and B, that the first two groups, those numbers match up to the group numbers. So 1 and 2, what is that? You're going to see that right here, these two numbers, they match up. Okay? And the reason why is because, well, each one of those groups has the same number of valence electrons. So group 2, they'd have 2 valence electrons. Now where it differs a little bit is when you get past that point. Okay, see, when you get past that point, we tend to leave off the group B elements right here. We tend to leave those out when we're looking at just the group A's. Now, if we look at the group A's, again, that matches with the number of valence electrons it has. Otherwise, what you'd be looking at is something like this right here. Okay? So, again, it's just two different ways that you can describe what group that you're looking in. If there's no letter, you go strictly by the column. If it has a letter, you need to look at my periodic table to indicate which column you're looking at. Okay? With those groups, if you choose to use the 1 through 18 method, then the first two groups, the alkalis, the alkali metals, they're going to have 1 valence electron. And then in group 2, the alkaline earth metals, they're going to have 2 valence electrons. And then when you get over to the other side of the periodic table, those nonmetals, if you have your halogens, group 17, those are going to have 7 valence electrons. Okay? Or you could describe them as 1A, 2A, and 7A, respectively. All right. Now, how might I give you this in terms of a quiz? These groups and periods. Well, can you describe to me what group and period oxygen would be in? We could say that oxygen, it's in group 6A, or we could say it's in group 16. All right, so that's our group right here. And then what period is it in? Well, it's in the second row of our periodic table, so period 2. So if we take magnesium, how would we describe it on the periodic table? Well, it's in group 2A or group 2. And then what row is this on? Well, it's in the third row, so period 3. All right, pretty easy to do. Now, valence electrons. Valence electrons, they're going to increase from left to right across the periodic table until we get to 8. All right, if you have 8 valence electrons, such as neon, you're going to have a stable element. All right, so anything less than that, these right here, these would be described as unstable in nature all the way up to 8. So these will all react with things. Neon does not want to react with anything. All right, what do we want to get from this? Well, with our valence energy level electrons, those valence electrons, lithium wants to lose 1 electron. Fluorine wants to gain 1 electron. Oxygen, it wants to gain 2. Nitrogen, it wants to gain 3, and so forth. All right, so those valence electrons that are going to exist at different energy levels, they just repeat each other. So if we go down in energy level and we now look at sodium, it's going to have 1. We go down in energy level and we have argon, it's going to have 8. Okay, so we have this repeating pattern, periodic pattern that occurs. Next, we have the number of valence electrons remains the same as you move down the table. Right? We've said this several times. We have our alkali metals right here. All of these are the alkali metals. Notice I did not lump hydrogen in here because hydrogen is not an alkali metal. Hydrogen's at oddball. All of these are in group 1. All of those then have 1 valence electron. But what's different? What period it's in. They're found in different periods, but they share characteristics that are the same because they all have 1 valence electron. Now, if we don't have that octet or 8 electrons, these elements are said to be unstable. They're going to form chemical reactions. Now, when they form chemical reactions, they're going to lose or gain electrons. If they lose or gain electrons, what we form is an ion. So we go from something that's an element found on your periodic table. Let's take sodium, for example. No, let's use lithium because this is going to be easier. See, lithium, it has 2 energy levels, and it has 3 electrons. Now, what lithium wants to do is it wants to be stable. But if it just has 1 electron in its outermost shell, it's not stable. So what it wants to do is what every metal wants to do. It wants to give away electrons. And if it gives away its electron, we're left with a stable element now. Now, you might say, wait, that doesn't have 8. Well, you got to remember, how many electrons can fit onto that innermost energy level? Only 2. It's filled. It's happy. It doesn't want to do anything else. Now let's look at one that would have 8 in its outer energy level. That would have that octet. Let's take a look at sodium. Sodium, we find it is going to have 11 electrons. So if it has 11 electrons, it's going to have a Bohr model, something like this. It's not stable. It's very reactive. Why? Because it has this 1 outer electron right here. So what do all metals want to do? Metals want to give away electrons. So that sodium atom, in order for it to become stable, it needs to lose this electron. Now, if it loses that electron, what do we notice? It now has 8 valence electrons. And it wants to have 8. It wants to have an octet in order to increase its stability, to make it more stable. All right, now those ions, as you're losing or gaining these electrons, what we're going to find is that if you lose electrons, they're going to become more positive because you're getting rid of negatives. And then the opposite of that, if you're adding electrons to something, if you're adding electrons, let's take, for example, fluorine here. Fluorine, you have for it, you've got something of a Bohr model that would look like this. All right, well, fluorine, it's missing an electron right here. So if this electron right here is added to this, see how it becomes more negative? We have this negative here. That negative gets added to this. So what we form is a negative ion. Okay. Those numbers that we're playing with here, the pluses and the minuses, they're known as the valency of our overall ion's charge. Now on my periodic table, you're going to find all of those values in the upper left-hand corner. So right here, sodium, what does it want to do? It wants to lose a negative. If it loses a negative, it becomes more positive in nature. Magnesium, it has 2 valence electrons. It wants to get rid of those 2. So if it gets rid of 2 negatives, it becomes more positive by 2. On the other side, fluorine, we said that it gains a negative. Chlorine gains a negative. Oxygen gains 2 negatives. What in the world? There's no number right here. Well, if you're looking at neon, it has 8 valence electrons. So does it want to pick up anything? No, No, it doesn't. That's why there is no oxidation number there. There is no valency number there because it doesn't want to form bonds with anything else. It's stable. It has its octet already. So let's move on to the next page. The next page, ooh, that is ugly here. Let's try to move this out of the way. Okay, there we go. All right, now, if we have these positively charged ions, things that are losing electrons, what is the reasoning for this? Well, let's take a look at potassium. See, potassium, it has 19 protons, 19 electrons. You're going to notice that this electron right out here, that makes potassium extremely unstable. All right, you can't hold raw potassium without it wanting to react with the moisture in your hand. Okay, so raw potassium, oftentimes it has to be stored in oil because oil and water don't mix. All right, so this potassium right here, what does it want to do? It wants to get rid of a negative charge. It wants to get rid of an electron. Well, if it starts out with 19 protons and it has 19 electrons at first, it's electrically neutral. It's just a potassium atom. So this is a potassium atom. All right, now, potassium wants to lose an electron. It wants to get rid of this. Bam, we got rid of it. It's gone. It left. It's forming an ionic bond with something else. All right, so we still have the 19 protons, but now because we got rid of an electron, now all of a sudden you end up with a +1 net charge. This is called a potassium ion. Okay, see the difference? The difference is that right here you have an atom, because it's electrically neutral, found off the periodic table. It's chemically unstable. Now over here we have lost an electron. Now we call it a potassium ion. Now that potassium ion, there is a specific name that's associated with these positively charged ions. It's called cations. They lose one or more electrons. Now those cations have fewer electrons and protons. That's what gives it its overall charge. All right. So you can see in the picture that when potassium becomes an ion, it loses its lone electron in its valence shell. That makes our potassium still have 19 protons, but now it only has 18 electrons. That's where you get the +1. And it's real easy to remember that these positively charged ions, they're called cations because look, you got a plus right there. The T, that's your plus. Okay. Now, on the opposite side, if you have anions are negatively charged ions because you're gaining one or more electrons. So that makes them more negatively charged. So right here, you're going to notice that fluorine at first, you have 9 protons, you have 9 electrons. We have a net charge of 0. This is a fluorine atom. Now, it's not chemically stable. That's unstable. Electrically neutral, yeah. Chemically stable, no. Okay, so what does this guy want to do? It wants to add an electron. Okay, so if it adds an electron, we now have 10 electrons. Well, you do the math, it comes up to be -1. This is an ion. And more specifically, it's called an anion because we've gained one more electron. Okay? So, if you form these ions, let's take a moment and just look at the names. See, I said that we have a potassium atom and then we had a potassium ion. When you form these chemical bonds, you do not change the name of the metals. So barium, if barium is going to form a chemical bond with something else, you would say that it is barium. You don't change the name at all. Don't do it. If we have an anion, a non-metal that's going to form a chemical bond, how do you know that it's bonded with something else? What you do is you change the suffix of it. So fluorine up top, fluorine, we gained an electron. How do I know that we formed, let's say lithium and fluorine, they combine together? If lithium and fluorine combine together, so lithium is going to give away its electron to fluorine. How do you know? You don't say lithium fluorine because those are just two atoms. What you say is that you have lithium, fluor, and then you replace the suffix with an IDE. The IDE tells the reader that you have an ion, and that ion is formed because you formed an ionic bond. Lithium gave away its electron to fluorine. The lithium, you do not change the name of the metal. You change the suffix of the non-metal. Okay, so you'd have fluoride. If we'd have magnesium and oxygen, I heard one time that magnesium and oxygen, that they were dating each other. See, if you have magnesium and oxygen, they start dating each other. And my first response was, OMG. That's actually bad. You don't write it down that way. See, magnesium, you always put the metal first. So that joke in itself is terrible, not just because it's a bad joke, but because it's written wrong. You can't put a non-metal first. You always, always, always put the metal first. So this would be, if I get my pen, magnesium. You don't change the metal name. And since magnesium bonded with oxygen, we would say oxide. Okay? So that's our naming of simple ionic compounds. All right. Now, let's take and just go over this one last time. If you have lithium, lithium's atomic number is 3. That means it has 3 protons with it. That means that it has 3 electrons with it. That is electrically neutral off the periodic table. That guy right here is unstable. Okay, so how does it become stable? Lithium needs to lose that 1 electron in its outermost shell. If lithium loses that 1 electron in its outermost shell, it becomes more positive by 1. This is stable right here. Okay, so that's why it has an overall charge of positive 1. If we look at this in terms of a seesaw, okay, at first you have a Bohr model of lithium. It's unstable because it's got that 1 outer electron right there. If it gets rid of that outer electron, you have fewer electrons than protons. That's why it is more positive by 1. All right. We'll go to another example of this. If we're looking at our oxygen atom right here, oxygen's atomic number is 8, so 8 protons, 8 electrons. It's electrically neutral. That means that this thing right here, because it doesn't have an octet of electrons, it's unstable. Octet of electrons, 8. We have 6 outer electrons right here. So those 6 outer electrons, you need to gain 2 more. We need to add an electron here. We need to add an electron here. Well, if we add 2 electrons, we now have 10 electrons. That means that this thing has become more negative by 2. Okay? You've added 2 negatives, added 2 negatives. I hope that makes sense. So our seesaw here, if we're looking at counting these up, you're going to have 1, 2 extra electrons that you add to this. 2 extra electrons, overall charge, -2. That's called an oxide ion once it's bonded with something else. We're now at the last part. We're going to finish up the periodic table looking at the trends that occur. So we've just finished up looking at what are called cations and what are called anions. We have cations and anions because the elements on the periodic table may not have an octet of electrons, 8 valence electrons, to make the elements chemically stable. So whenever you're looking at metals, whenever you're looking at metals, and again, metals are going to be to the left of this stair step. So all of these guys right here, all right, all of those are going to form what are called cations. When you're naming these, you do not change anything with the metal at all. If beryllium is going to combine with fluorine, then we'd say beryllium at first. You always start with the metal. And then the anion, when it bonds with that, all of the nonmetals are to the right of the periodic table. So we'd have beryllium and fluorine, they combine together to form a stable compound. So that would be beryllium fluoride. All right. Now, when we're forming these cations, you have to remember that they are going to be positively charged in nature, and they're going to match up with whatever group A that they're in. So this is group 1A, so it has +1. Beryllium, it's in group 2A, so it would be a +2. All right. The easy way to remember that you're looking at cations being positive, you have the plus for the T that tells you that that thing has lost electrons, becoming more positive in nature. On the right-hand side, those anions, they gain electrons, so it would be a -1, -2, and that would trend all the way down the periodic table. So our ionic trends, toward the left-hand side of the periodic table, you have cations. On the right-hand side of the periodic table, you have anions. The cations, whatever group they're in, they're going to tell you the same number of valence electrons that they need to lose. All group 1 needs to lose 1. All group 2 needs to lose 3. All group 6, group 6A right here, all of those need to gain 2 electrons. Okay, let's take a look at a couple other trends. All right, so a couple other trends on the periodic table. We're talking about atomic radius. That one will probably be the easiest one to start with because everybody has some idea of what a radius of a circle is. So when we're talking atomic radii, it's just a little different. See, when you're looking at atomic radii, if you have an atom and we're trying to measure from the center out to the edge, how do you know distinctively where that outer edge is? Because those electrons are always moving around. Okay, that's based on probable locations. So what we do to figure out atomic radii is you take 2 like elements. So let's say that this is hydrogen, a hydrogen atom. Okay, how do we find out what the atomic radii is? Well, we look at the distance between the 2 nuclei. That's not going to change. So if we look at the distance between these 2 nuclei and then cut it in half, you now have the atomic radii. All right, so let's start with that one. So the atomic radii, if it's half the distance between 2 nuclei of our atoms, and I use the example of the hydrogen atom, we're going to measure that distance. Since it's going to be super, super small, we're going to measure that in what are called picometers. Now on my periodic table, what you're going to find is that particular number, that distance, is going to be given to you in your cells. So from the key here, we see that boron, its atomic radii would be 85 picometers. If you're looking at carbon is 77, nitrogen 75, oxygen is 73. So what's the trend that you're noticing? As you're moving from left to right across the periodic table, the radius gets smaller. Your atom's size gets smaller and smaller and smaller. How about if we go down the periodic table? Well, again, boron, it's got 85. Aluminum, 143. We have gallium, 135. You have indium, 167. Now, you might say, well, it's not a distinctive increase. So here we had it increasing, then that one decreases, and then this one increases again. What we do is we look at the general trend of what's happening. The general trend, as we move down the periodic table, the general trend is that it gets larger. So let's look at one more before we go back. We have 73, 103, 119. So the general trend as you move down the periodic table is that the radius of your atoms on that periodic table are going to increase on the way down and decrease on the way over to the right-hand side. All right. So let's take and look at why these atoms keep getting smaller as they move from left on the periodic table to the right on the periodic table. We'll start off looking at lithium. Lithium, it has 3 positive charges in the nucleus. You move over to the right-hand side, and let's take a look at fluorine. Fluorine has 9 positive charges in the nucleus. So why is lithium larger than what fluorine is? Well, I want you to think of this in terms of magnets. The magnets, you have 3 positive charges right here in the nucleus of the atom. They are pulling inwards on these electrons. All right, so if you only have 3 positive charges and you're pulling inwards on those electrons, it's not like it's a strong magnet. You don't have a strong nuclear charge. But if you go over to fluorine, on the other hand, fluorine now has 9 protons, has a stronger nuclear charge. So if we're looking at trying to pull these electrons in towards the nucleus of the atom, you have, in essence, a stronger magnet pulling these things inwards. So that shrinks up the radii. Now that has a lot of implications here, and we'll take a look at those when we go to our other periodic trends. All right, so as we have more protons that are added to the nucleus, they provide a stronger positive attraction for the electrons. It pulls them in. So the distances as we have these electrons that are being pulled in closer and closer, you're going to find that the radius decreases as you move from left on the periodic table to the right. What I have here is just a little graphic that shows you this change in radius as you move across the periodic table. So if I zoom in just a little bit, you can see that on the left-hand side, here we have lithium, and then way over here, you got that little spot, that would be fluorine. Now, how about if we move down the periodic table? Why do the atoms keep getting bigger as you move down the periodic table? This is going to be super easy, okay? When you are looking at the principal quantum number, you're looking at the number of energy levels. So on the first energy level here, you have 1 ring. On the second energy level, you have 2 rings. On the third one you have here, you have 3 rings. Pretty easy to see why you have an increased radius as you move down the periodic table, because you have more energy levels. Now, the second thing that you're going to increase in on is as you start to put in your electrons here, well, electrons are negative, right? So each one of those little dots that I put in there, they're repelling each other. So if the center of your magnet, that green little dot right there, if that is pulling the electrons in, and you have these right here that are repelling the outermost electron, well, then it's not going to be held as tight. So it's going to be loosely held. It's going to be out away from the nucleus a little bit more because of what's called shielding. And that's going to be another one of our periodic trends in just a moment. All right, so the radii. With subsequent groups, the atomic radii increases since the electrons occupy higher energy levels. This results in electrons being further away from the nucleus, and the positive attraction from the proton is therefore less, so the electrons spread out further. All right, so as you are moving through your groups, what we're going to find is that as you move from right to left, as you go from right to left, what this means is that you're going to see the radius of your atom getting bigger and bigger and bigger. Okay? And then as you move down the periodic table, likewise, your atoms are going to get bigger and bigger and bigger. Okay? If lithium wants to remove an electron, it doesn't just happen on its own. See, what you need to do is you need to have some energy in order to pull that electron away. So let's take a peek at our Bohr model to help us understand this. Inside the nucleus of your atom, you have 3 positively charged protons. And it's pulling on this electron that's out here. All right, now, if you think of this in terms of magnets now, this is your refrigerator right here, that +3, and you've got a magnet that's out here. If you're trying to remove the magnet from the refrigerator, you can do that, all right? But you have to apply some energy to pull that electron away. So that is what we refer to as the ionization energy, the energy needed to remove an electron from that outermost energy level. So the lower the ionization energy, the easier it is for an atom to lose its electron. So where would we find the ionization, the energy needed to remove an atom to be the lowest? Well, you could look on the periodic table, and what you're going to find is that right here, you're going to have that number given to you. All right, kilojoules per mole. So you could look through this whole thing, but let's think about this. Where would the magnet on your refrigerator be easiest to remove? When it's close to the refrigerator or when it's further away from the refrigerator? Well, if you're holding the magnet far away from the refrigerator, there's very little attraction to it. So what element has the largest radii? Francium. Francium, you've got 7 energy levels that are going to be associated with francium. So we have 2, 3, 4, 5, 6, and 7. And its one single electron is right here. That is a heck of a distance away from the positive core of francium. So if you have a great distance in between the positive and the negative, it's not going to be held on very tight. So francium is going to be the most reactive metal that you're going to find on the periodic table. Why is that? Because it has the greatest atomic radii, and it's also, I want you to think of this too. What do you have in between this single electron here and the 87 protons in the nucleus? In between there, you have 86 other negative charges that are shielding this electron from the positive core. All right, so I keep hitting on this term shielding because we are going to come right back to it. So generally speaking, elements on the left-hand side of the table are metals. They're going to have the most empty valence shells. They're going to have the fewest number of electrons in its outermost energy level. So that means they are going to have the lowest amount of ionization energy. All right. So why then are the ones on the right-hand side going to have a higher amount of ionization energy? Why is it going to be so hard to pull electrons away from fluorine? Because fluorine is so tiny. Fluorine, it's got 7 outer electrons that are held very close to the nucleus. It's going to be super hard to try to get rid of them. So on the right-hand side of the periodic table, you have higher ionization energies. So that's why they look to gain electrons versus wanting to lose electrons like your metals. All right. Therefore, ionization energy increases as you go from left on the periodic table to the right. Now, you are going to notice that the noble gases, they have extremely high ionization energies. Why is that? Do they want to form compounds? No, they're chemically stable. They don't want to do that. All right, here we go. Electron shielding. Electron shielding is going to affect your ionization energy. What exactly is this shielding, this electron shielding? Again, if you think of it as francium, all the way down here at the bottom left of your periodic table, we have 4, 5, 6, and 7. It has one valence electron that it wants to get rid of. Is it going to take a lot of energy to get rid of that? No. The electron is very far away from that 87 protons. In addition to that, in between here, you have 86 other negative charges that are repelling each other. So this provides a great deal of shielding, and therefore it decreases the energy needed to remove that outermost electron. So as you move from right, or move to the right across the periodic table, the number of electrons, it increases, and so the strength of shielding is going to increase also. The more electrons you have, the more shielding that you're going to have. And that means that as you move down the periodic table, those ionizations are going to increase for your metals. Okay? So this is a good look at what the general trend of ionization energies are. Okay? All right, moving on. We have electronegativity. Electronegativity is the relative attraction that two elements are going to have when they go to bind together. All right, so when these elements are going to attract each other, what is the likelihood of one element attracting another's electrons to them? All right, so I want you to think of this for 1 second. I'm going to put a example up here on the screen for you. Let's take a look at this in action. If you have a lithium atom and a fluorine atom, why are the electronegativities different? The electronegativities have to deal with this idea of attractiveness, right? So if we're trying to attract electrons to an atom, where will the electron be most likely attracted to? It would be attracted to the radius that is the smallest. Think of it as you trying to get a magnet to stick to the refrigerator. The closer you are to the refrigerator, the easier that electron will stick to it. So with fluorine and lithium, there are values on the periodic table, and they are found in the upper right-hand corner of each cell. Now you're going to notice like argon doesn't have one because argon doesn't want to attract anything to it. It's stable. So fluorine has the most attractiveness associated to it than any other element on the periodic table. Why is that? Because it's the smallest radii. So the closer you are to the nucleus, the greater the attraction you're going to have. So this guy right here, fluorine, has an attractive value of 4. That's its electronegativity. Lithium, on the other side, if we look at it, it says it has a value of 1. All right, now these numbers that we're throwing up here, let's take and think of it not as electronegativities, but as numbers that you guys might associate with somebody that you find attractive. If you find somebody that's attractive, you'd rate them as like a 10. Ooh, hot stuff. Okay, well, here in terms of the periodic table, this is your quote-unquote 10. Fluorine is the most attractive element on the periodic table. Why? Because the electron it's trying to attract would be closest to the positive core. If you're looking at francium way down here, that thing is so far away from the nucleus, and there's 86 electrons repelling it. There's no way that you're going to get in a very strong attraction to pull electrons to francium. All right, so what we do when we're trying to determine what type of chemical bond you have, you subtract those two values. You come up with what's called a change in electronegativity of 3. On the back of my periodic table, that says that that's going to form an ionic bond. So we have fluorine that's going to be attractive enough. See if I can grab this electron here. Fluorine is going to be attractive enough that it's going to strip the electron away. It's going to come all the way over here, and now it's bound to fluorine. We formed what we would have here as an ionic bond. Now, why is that called an ionic bond? Because this guy right here, this now is a lithium cation. This right here, this is a fluorine anion. And if we were going to name this type of compound, we would say that this is a lithium fluoride compound. Why do I put the IDE? So that way I know that that thing has chemically bonded with something else. All right. So what we should notice before I go any further is let's look at a trend here. What happens when ions form? What's going to happen to the size of this guy right here? Well, if we remove the outer electron, that shell isn't there anymore, right? So that thing got smaller. Cations, they get smaller. Cations get smaller. So what do you think is going to happen if you add more negatives to the anion? If the cations get smaller, the anions, there's more negative charges there, there's more repulsion. You're going to have an anion that's going to get bigger. Next thing, in contrast, it's more energy efficient for elements on the right-hand side of the periodic table to gain electrons to fill its outer shell. Why? Because they're more attractive. They're going to pull electrons to them easily. They do not want to lose 7 electrons for those halogens. They just don't want to do it. There's too much energy trying to pull that away. So we have atoms which have a tendency to gain electrons to fill their outer shells are more electronegative. They're more attractive. So electronegativity increases from left to right. By contrast, as you're moving down the periodic table, the atomic number increases, the radius increases, the shielding increases. So that makes francium the ugly one of the periodic table. It's not going to be very attractive. It does not want to attract any electrons to it at all. It's a metal. Metals want to give away electrons, not gain them. All right. So there's our general trend right here. All right. We're getting on to our last ones here. We have electron affinity. Well, ionization energy was related to pulling electrons away. Well, the anions, they have to gain electrons. That just doesn't happen, all right? So electron affinity is the ability of an atom to accept an electron, all right? So unlike electronegativity, electron affinity is a measure of the change in energy that results as we add electrons to it. So as you move from left to right across the periodic table, the electron affinity increases also. So more and more and more energy is going to be released as we form a bond, as we add electrons to the, let's say, the halogens, all right? So therefore, the electrons, to move closer to the nucleus, electron affinity decreases as you go down a group. And again, they don't want electrons. If you're looking at francium, rubidium, they don't want electrons. The larger they are, the more likely they are to give them away, not gain them, okay? And truthfully, when you're looking at electron affinities, they're kind of difficult to determine when you're looking at, let's say, francium as an example, because francium does not want to gain an electron. So if affinity deals with energy associated with adding electrons and francium doesn't want it, it's kind of difficult to get that. All right, so here's our general trend right here. Melting points, what we're looking at here is more or less the amount of energy needed to break the bonds in order to have a phase change, okay, from a solid to a liquid. So in general, if we're looking at the stronger bonds between atoms, the more energy is needed to break those. But when we're looking at general trends, there isn't any noticeable one. But what we do say is that when you're looking at metals, metals have high melting points. So anything in terms of a trend would be related to anything on the left-hand side of that stair step. It's going to have relatively high melting points. And then the nonmetals on the right-hand side, they're going to have relatively low melting points. So a nonmetal like carbon would have a high melting point. You're looking at a metalloid such as boron. That's going to be a real high melting point. So when we're looking at these, you just have to go to the characteristics of metals and nonmetals that I mentioned before. All right, now the metallic characteristics. I've said this countless times. Metals want to lose electrons to form cations or positive ions. So as you move to the right of the periodic table, you're changing from metals to nonmetals. That means that your characteristics is decreasing. So on the left-hand side, you're going to find more metallic characteristics as you go to the left-hand side. From right to left, the metallic characteristic is going to increase. All right. The more loosely those electrons are held, the more metallic you're looking at. And then as you move down the periodic table, the more metallic the elements become because you have a larger radii, electrons are more loosely held. So the most metallic element on the periodic table would be that francium.